Here's a quick little video about two very cool things about a couple of quadrics. We know that this guy is the hyperbolic paraboloid, or the saddle, or if you chop it off so that it's kind of circular from the top, it's a Pringle. And we know there's a cool thing about the saddle surface, that there's a straight line that goes through here and a straight line that goes through here. There's an X that if you basically look at the contour, you can even see it. If you look at the contours, that's kind of the greenish to green-blue transition. There's this X in the contour plot. Everything else, all the other contours are hyperbolas. They are not straight lines, but there's these two straight lines that live on the surface. Now, in fact, that's part of a huge family of straight lines that does much more. So what I want to show you is I'm going to show you all these straight lines. They may not look right now like they're on the surface, but if you look at it from the right perspective, you can see that they actually do lie in the surface. They actually, wasn't careful to get them to stop where the graph of the hyperboloid stops, so it looks like they go off. But remember, the hyperboloid just continues. So I'm going to continue. What it turns out is what these are doing is they are getting kind of less steep as they go. They're all exactly on the surface. And just about the last one I did is one of the ones that I already mentioned. It's actually it's a level curve. It's actually flat, totally horizontal. And then I can keep going the other side. And what we discover is that the entire surface, even though it's a curved surface, the entire surface can be made out of just straight lines. That's really cool. It's called a ruled surface, and it's a particularly nice example of something you think about in algebraic geometry, where you really get very deep into the connections between algebra and geometry. Now, that's cool enough, but if you think about it, you might want to pause the video. There's a symmetry here that the saddle surface has. There's a lot of symmetry that the saddle surface has, that these lines break that symmetry. So you might want to think, does that suggest there's something missing to this picture? All right, I'm sure you paused the video and thought about it for a little bit. So now I'm going to finish these lines. What's true is that there's another family of lines that does it exactly just kind of the opposite way, symmetrically. It's basically taking the other lines and just flipping around the vertical axis. To me, this looks like a really good way to construct a bandage. I'm not sure why a bandage comes to mind. It's also a really good way if you have a bunch of steel girders. If you want to create a delicate looking and graceful curved shape out of very strong straight lines, this is a great way to do it. And this definitely shows up in our architecture a fair amount. Okay, so that's pretty cool. Now, I claim the same thing is true for the hyperboloid of revolution, of one sheet. If you look at this, if you pick a line that goes just exactly in the right direction, that straight line actually manages to just exactly be on that surface. It's very important that this is perfect. This has to be the perfect hyperboloid that's actually described by a quadratic equation, the actual quadric. If it's something that just vaguely has this shape, it's not going to actually have that straight line in it. Well, now, hopefully, the symmetry here makes it pretty clear. If that one straight line shows up, well, why can't I just rotate it around and rotate it and rotate it and rotate it? And indeed, I can cover the whole surface with rotated copies. Okay, so I can create this curved shape again out of straight lines. It's a ruled surface, but it's all. Oh, and I should have mentioned this for the hyperbolic paraboloid. It's what's called a doubly ruled surface. There's two distinct families of lines. You just flip them over, just like on the hyperbolic paraboloid. And so that's a very good way to create a curved shape, which has a lot of wonderfully nice properties. If it looks like a cooling tower from a nuclear plant, that's not an accident. You're creating this curved shape out of straight lines, which are easy to make very strong out of, say, iron girders. So again, it shows up in those kinds of architectural forms. Very cool. And I think rather unexpected when you start looking at a curved surface that it could be possibly made out of straight lines, and not just in one way, but in two.